For centuries, humans looked up at the Milky Way and saw only a river of light across the night sky. The ancient Greeks called it Galaxius Kyklos, the Milky Circle. The Vikings saw it as the path to Valhalla. The Aboriginal Australians traced the shape of an emu in its dark patches. But no one suspected they were looking at bones. The discovery of the Milky Way's skeletal structure began not with optical telescopes but with radio waves and infrared light, wavelengths that can peer through the cosmic dust that obscures our view. In the 1970s, radio astronomers started mapping clouds of molecular hydrogen, the raw material from which stars form. They found filaments, long, thin structures of gas, but assumed they were random, like clouds on Earth. Everything changed with the launch of space telescopes that could map the galaxy in 3 dimensions. The Herschel Space Observatory, operating from 2009 to 2013, revealed that these filaments weren't scattered randomly. They were organized into vast networks, like a cosmic web within our galaxy. But it was the Gaia mission, launched in 2013, that truly exposed the bones. Gaia measures the precise positions and movements of over 1 billion stars. By tracking how stars move, astronomers can infer the gravitational structure of the galaxy, including invisible dark matter and gas clouds. It's like doing an MRI of the Milky Way, revealing internal structures we couldn't see before. Dr. João Alves at the University of Vienna was among the first to recognize what they were seeing. These aren't just filaments, they're load-bearing structures. They're the galaxy's skeleton, holding everything in place while allowing for movement and growth. The first confirmed bone was a structure now called the Nessie Nebula, formerly designated as a giant molecular filament, GMF. It stretches over 500 light-years in length, but is only 1 to 2 light-years wide, proportionally thinner than a human hair. If the Milky Way were shrunk to the size of Earth, Nessie would be like a single fibre of spider silk. But Nessie wasn't alone. As astronomers looked closer, they found bones everywhere. The Radcliffe Wave, a 9,000 light-year-long undulating structure of star-forming regions, discovered in 2020, that includes the Orion Nebula and rises 500 light-years above and below the galactic plane like a cosmic sine wave. The Cat Tail, a massive structure over 5,000 light-years long, possibly the largest coherent structure in our galaxy, discovered in 2021. The Maggie filament, the longest known coherent structure in the Milky Way at 3,900 light-years, composed almost entirely of atomic hydrogen. Dr. Jonas Said at the Max Planck Institute for Astronomy, who discovered Maggie, describes the moment of realization. "I was looking at the data, and suddenly I could see it. This impossibly long, impossibly straight structure. It was like finding a highway in what we thought was wilderness. These bones aren't passive structures, they're active sites of star formation, channels for gas flow, and gravitational anchors that shape how our galaxy evolves. They're also surprisingly fragile. Despite spanning hundreds of light-years, they can be disrupted by stellar winds, supernovae, or gravitational interactions, and many of them show signs of being broken. To understand what these cosmic bones really are, we need to zoom into the molecular level, or at least as close as we can get when dealing with structures light-years across. A galactic bone is primarily made of molecular hydrogen, H2, 2 hydrogen atoms bound together. This is the most abundant molecule in the universe, but it's incredibly difficult to detect because it doesn't emit radiation at temperatures typical of interstellar space. We can only see it indirectly, through tracer molecules like carbon monoxide, CO, that glow in radio wavelengths. The density in these bones is extraordinary by interstellar standards, but would be a better vacuum than anything we can create on Earth. A typical bone contains about 100 to 10,000 molecules per cubic centimetre. For comparison, the air you're breathing contains about 10 to the power of 19 molecules per cubic centimetre. Yet despite this incredibly low density, the sheer volume of these structures means they contain millions of times the mass of our Sun. Dr. Cara Battersby at the University of Connecticut studies the internal structure of these bones. They're not uniform. They have a spine of denser material running through the centre, surrounded by a more diffuse envelope. Along the spine, you find knots and clumps. These are where stars are being born. The temperature inside a bone is brutally cold, typically 10 to 20 Kelvin, negative 440 degrees Fahrenheit to negative 420 degrees Fahrenheit. At these temperatures, atoms move so slowly that they can stick together when they collide, forming molecules and dust grains. The dust is crucial. It provides surfaces where molecules can form and shields the interior from radiation that would destroy complex molecules. But the most fascinating aspect of galactic bones is their magnetic field structure. Magnetic fields thread through these filaments like invisible rebar, providing structural support against gravitational collapse. Dr. Huabai Li at the Chinese University of Hong Kong has mapped these magnetic fields using polarized light. The magnetic fields are remarkably ordered, all aligned along the length of the filament. It's like nature's version of carbon fiber, incredibly strong in one direction. This is what allows structures only a light year wide to stretch for hundreds of light years without collapsing. The formation of these bones is still debated, but several mechanisms are likely involved. Gravitational instability. In the galactic disk, gravity can cause gas to collapse into filaments rather than spheres, especially when rotation and magnetic fields are involved. Converging flows. Where streams of gas in the galaxy collide, they can compress into dense filaments. Like rivers converging, but in 3 dimensions and with gas instead of water. Spiral arm compression. As gas orbits the galaxy, it gets compressed when passing through spiral arms, potentially triggering filament formation. Turbulent fragmentation. The chaotic motions in the interstellar medium can create density fluctuations that grow into filaments. Dr. Rowan Smith at the University of Manchester simulates bone formation. It's not one process, but a symphony of physics. Gravity, magnetism, turbulence, and rotation all play together. Change any one factor, and you might not get bones at all. The life cycle of a galactic bone is measured in millions of years. They form from converging gas flows, grow by accreting more material, spawn stars along their length, and eventually disperse, blown apart by the very stars they created. It's a cosmic Ouroboros, the snake eating its own tail. Of all the structures discovered in our galaxy's skeleton, none is more significant for Earth than the Radcliffe Wave. This undulating chain of star-forming regions passes remarkably close to our solar system, within 500 light-years at its nearest point. And it's broken. Discovered in 2020 by Dr. Catherine Zucker and her team at Harvard, the Radcliffe Wave redefined our understanding of the local galaxy. What astronomers had thought were separate, unrelated star-forming regions, including famous nebulae like Orion, Perseus and Taurus, turned out to be connected pearls on a single cosmic string. It was hiding in plain sight, Zucker explains. We'd been looking at these star-forming regions for centuries, but we couldn't see the connection until we had 3D positions from Gaia. It's like those magic eye pictures. Once you see it, you can't unsee it. The wave is vast, 9,000 light-years long, 400 light-years wide, and oscillating 500 light-years above and below the galactic plane. If you could see it with the naked eye, it would stretch across most of the night sky. Its mass is equivalent to 3 million suns, mostly in the form of gas and dust. But here's what makes the Radcliffe Wave special. It's not just near us, it's interacting with us. Our solar system appears to have passed through the wave about 13 million years ago, and will pass through it again in another 13 million years. We're literally surfing along a galactic wave. Dr. João Alves, who collaborated on the discovery, points out the implications. The Radcliffe Wave is our cosmic neighborhood's dominant structure. It affects local star formation, the distribution of gas and dust, and possibly even the flux of cosmic rays reaching Earth. We don't just live near it, we live with it. The wave shows clear signs of damage. In several places, the continuous structure is broken, with gaps where material has been blown away or gravitationally stripped. The most significant fracture is near the Orion molecular cloud complex, where a series of supernova explosions over the past 10 to 20 million years have blown a cavity in the structure. This cavity, called the local bubble, is where our solar system currently resides. We're living inside a fracture in a galactic bone. Dr. Alyssa Goodman, who leads the team studying these structures, explains, "The local bubble was blown by at least 15 supernovae over millions of years. These explosions cleared out the gas and dust, creating a cavity about 1,000 light-years across. The walls of this bubble are where new stars are forming now, compressed by the expanding shockwave. The fracturing of the Radcliffe wave might have been crucial for Earth's existence. The supernovae that created the local bubble also enriched the surrounding gas with heavy elements, the carbon, oxygen, silicon, and iron necessary for rocky planets and life. Without this cosmic bone and its violent fracturing, the solar system might never have formed, or might have formed without the elements necessary for life. Recent observations from 2024 show that the Radcliffe wave is not static, it's oscillating. Like a rope being shaken, the wave undulates through space with a period of about 50 million years. This oscillation might be driven by gravitational interactions with the galaxy's spiral arms, or by dark matter structures we can't see. Dr. Ralph Konietzka at Harvard, who discovered the oscillation, describes it. The wave isn't just sitting there, it's dancing. This motion affects everything around it, creating zones of compression and rarefaction that trigger or suppress star formation. It's like the galaxy has a pulse, and we're measuring its heartbeat. The Milky Way's bones don't break gently. When these structures fracture, it's through violence on a scale that defies imagination. Supernovae, galactic collisions, and encounters with dark matter structures that remain invisible, even as they tear visible matter apart. The evidence for these fractures is everywhere once you know how to look. Dr. Anna Bonaca at Harvard discovered one of the most dramatic examples in 2019. A gap in a stellar stream called GD1, with stars scattered to either side like cosmic shrapnel. Something punched a hole through this structure, something massive and invisible. The only thing that could cause this kind of damage is dark matter, Bonaca explains. We're seeing evidence of a dark matter subhalo, a clump of dark matter about 1 million times the Sun's mass, that collided with the stream. It's like finding a broken window and deducing the size and speed of the invisible ball that broke it. These dark matter interactions are constantly fracturing the galaxy's visible structures. The Milky Way is surrounded by hundreds, possibly thousands of dark matter subhalos. Remnants of smaller galaxies are galaxy-consumed. As they orbit through the Milky Way, they leave a trail of gravitational destruction, breaking apart streams and filaments. But the most dramatic fractures come from the Milky Way's ongoing collision with the Sagittarius dwarf galaxy. This small galaxy has been falling into ours for billions of years, and each passage creates cosmic devastation. Dr. Vasily Belokurov at Cambridge University has mapped this destruction. Sagittarius has passed through the Milky Way's disk at least 3 times that we can trace. Each passage creates ripples, like dropping a stone in a pond. But these ripples are hundreds of light years high and contain millions of stars. The most recent passage, about 500 million years ago, might have triggered the burst of star formation that created our Sun. The gravitational disturbance compressed gas clouds throughout the galaxy, causing them to collapse into stars. We might owe our existence to a galactic collision. The evidence for these collisions is written in the galaxy's bones. Many of the giant molecular filaments show kinks, bends and breaks that align with the predicted path of Sagittarius. The Radcliffe wave's oscillation might have been triggered by one of these passages. Dr. Chervin Laporte at the University of Barcelona has simulated these interactions. Every collision leaves scars. Some heal, gas flows back, structures reform, but others remain as permanent fractures. Cosmic fault lines where the galaxy remains weak. Supernovae create smaller but more violent fractures. When a massive star explodes, it releases energy equivalent to the Sun's entire lifetime output in seconds. This explosion can punch holes through galactic bones, disperse molecular clouds, and trigger new star formation in compressed regions. The Orion Eridanus superbubble is a prime example. This vast cavity, over 1,000 light-years across, was blown by dozens of supernovae over the past 20 million years. The expanding bubble has fractured multiple galactic bones, including parts of the Radcliffe wave. Dr. Jennifer Cash at the Space Telescope Science Institute studies these superbubbles. Each supernova is like a cosmic bomb going off inside the galaxy's structure. The shock waves travel for hundreds of light years, compressing gas here, dispersing it there. Over time, multiple supernovae can completely reorganize the local galactic architecture.
But perhaps the most intriguing fractures are the ones we can't explain. Throughout the galaxy,
astronomers find breaks in structures that don't align with any known collision or explosion. These mystery fractures might be evidence of phenomena we don't yet understand. Dr. Eugene Vasiliev at the Institute of Astronomy in Cambridge studies these anomalies. Some fractures show characteristics we've never seen before, spiral patterns in the break, as if something twisted the structure as it broke. Others show evidence of reforming, as if the galaxy is trying to heal itself. We might be seeing new physics at work. The bones of the Milky Way aren't static. They're part of a vast circulatory system that moves gas, dust, and even stars throughout the galaxy. Like blood vessels in a body, these structures channel material where it's needed, remove waste products from stellar death, and maintain the galaxy's overall health. Dr. Mark Krumholtz at the Australian National University has spent years modelling this galactic circulation. The galaxy isn't just a collection of stars orbiting a centre. It's a living system with flows, cycles, and feedback loops. The bones are the highways along which material travels. Gas flows along these filaments at speeds of 10 to 50 kilometers per second, seemingly slow by cosmic standards, but these flows carry millions of solar masses of material. The gas movement isn't random. It follows specific patterns determined by gravity, magnetic fields, and the galaxy's rotation. The circulation has multiple components. Radial flows. Gas flows inward toward the galactic centre, feeding the supermassive black hole and central star formation. This inflow is balanced by outflows driven by stellar winds and supernovae. Vertical circulation. Gas rises out of the galactic plane, cools, and falls back down, a cosmic fountain that cycles material between the disk and halo. This fountain can launch gas thousands of light-years above the disk. Spiral flows. Gas follows the spiral arms, getting compressed as it enters them and expanded as it exits. This compression triggers star formation, which is why spiral arms glow with young blue stars. Filamentary flows. Along the bones themselves, gas streams from less dense to more dense regions, feeding star-forming cores. Dr. Naomi McClure-Griffiths at the Australian National University discovered that this circulation extends far beyond the visible galaxy. We found streams of gas extending 200,000 light-years from the galactic centre, twice the diameter of the visible disk. The galaxy is breathing, inhaling and exhaling gas on cosmic scales. This circulation is crucial for the galaxy's survival. Without it, all the gas would either fall to the centre or be blown away, and star formation would cease. The bones act as both structural support and circulation channels, maintaining the delicate balance that keeps the galaxy alive. The fractures in these bones affect the circulation profoundly. A break in a major filament can redirect gas flows, starving some regions of material while flooding others. It's like a broken blood vessel in the body, potentially catastrophic if not repaired. Dr. Françoise Colmes at the Paris Observatory studies how galaxies repair these breaks. Magnetic fields try to pull the fractured ends together. Gravity attracts gas to fill the gap. Sometimes new structures form to bridge the break. The galaxy has remarkable self-healing properties, though the process takes millions of years. Recent observations show that our local bubble, the cavity we live in, is affecting the galaxy's circulation patterns. Gas flowing along the Radcliffe wave gets deflected around the bubble, creating eddies and turbulence. These disturbances trigger star formation at the bubble's edges, while suppressing it in the interior. Dr. Douglas Finkbeiner at Harvard maps these flows. We're seeing that cavities and bubbles aren't just empty spaces. They're active components of the galactic circulation. They channel flows, create pressure differences, and drive gas movements across hundreds of light-years. The circulation also transports more than just gas. Cosmic rays, high-energy particles accelerated by supernovae and other violent events, travel along the magnetic fields in these bones. Heavy elements forged in stellar cores spread along the filaments. Even small dust grains surf along the gas flows. This transport is essential for life. The carbon in your body, the oxygen you breathe, the iron in your blood, all were created in stars and distributed through the galaxy by this circulation system. Without the bones and their flows, these elements would remain locked in stellar graves, unavailable for new worlds and new life. Beneath the visible bones of the Milky Way lies an even more fundamental structure, a scaffold of dark matter that shapes everything we can see. This invisible skeleton outweighs the visible galaxy by a factor of 10, and its gravitational influence determines where the visible bones can form. Dr. Gertina Besler at the University of Arizona studies this dark scaffolding. Dark matter is like the invisible framework of a building. You can't see it directly, but you can see how it shapes the visible structure. The galaxy's bones follow paths laid down by dark matter filaments billions of years ago. The evidence for this dark scaffold comes from multiple sources. The motion of stars reveals gravitational influences that can't be explained by visible matter alone. Streams of stars torn from globular clusters trace out invisible structures, like ribbons wrapped around an invisible Christmas tree. The most dramatic evidence comes from gravitational lensing. When we look at distant galaxies through the Milky Way's halo, their light gets bent by dark matter's gravity. By measuring these distortions, astronomers can map the dark matter distribution. Dr. Dennis Urkel at the University of Surrey uses stellar streams as dark matter tracers. Each stream is like 1,000 test particles dropped into the galaxy's gravitational field. By seeing how they move and spread, we can map the invisible forces shaping them. The dark scaffold isn't smooth, it's clumpy, with dense knots and filaments of dark matter threading through the galaxy. These structures formed first, in the early universe, with visible matter falling into their gravitational wells later. The correspondence between dark and visible structures is remarkable. Many of the galaxy's visible bones align with predicted dark matter filaments. The Radcliffe wave, for instance, follows a dark matter overdensity that might have guided its formation. Dr. Robin Sanderson at the University of Pennsylvania simulates this interplay. Dark matter creates the gravitational valleys that channel gas flows. Where dark filaments intersect, gas accumulates, forming the giant molecular clouds that become stellar nurseries. The visible galaxy is literally shaped by an invisible template. But dark matter doesn't just guide structure formation, it can also destroy structures. Dark matter subhalos, remnants of absorbed dwarf galaxies, orbit through the Milky Way like invisible wrecking balls. When they pass through visible structures, they can shatter them. The GD1 stream mentioned earlier shows clear evidence of such an encounter. The gap in the stream, with stars scattered to either side, reveals where a dark matter clump punched through. From the size and shape of the gap, astronomers can determine the mass and speed of the invisible impactor. Dr. Adrian Price Whelan at the Flatiron Institute hunts for these dark matter impacts. We're doing cosmic forensics, looking at the damage to visible structures to understand invisible objects. Every broken stream, every fractured filament might be evidence of dark matter structures we can't see any other way. The dark scaffold also affects the galaxy's future evolution. Simulations show that dark matter filaments channel the infall of gas from intergalactic space, determining where new material enters the galaxy. They also guide the orbits of satellite galaxies, setting up future collisions and mergers. Most remarkably, the dark scaffold might be evolving. Recent observations suggest that dark matter isn't completely collisionless. It might interact with itself in ways we don't understand. These self-interactions could cause the dark scaffold to evolve over time, slowly changing the gravitational landscape of the galaxy. Dr. Manoj Kaplinhat at UC Irvine studies self-interacting dark matter. If dark matter particles can collide and exchange energy, the dark scaffold would evolve. Dense regions would become denser, creating stronger gravitational wells. This could explain some of the structures we see that don't match cold dark matter predictions. Every fracture, every bend, every peculiarity in the Milky Way's bones tells a story about our galaxy's past. Like archaeologists studying broken pottery to understand ancient civilizations, astronomers study broken galactic structures to understand the Milky Way's history. Dr. Hans-Walter Rix at the Max Planck Institute for Astronomy pioneered this field of galactic archaeology. The galaxy remembers everything that ever happened to it, every collision, every burst of star formation. every close encounter with another galaxy. It's all preserved in the positions and motions of stars and gas. The archaeological record reveals that the Milky Way has had a violent past. The galaxy we see today is the product of countless mergers and collisions. Each interaction left its mark on the galactic bones. The most significant recent discovery is the Gaia Sausage Enceladus, the remains of a large galaxy that collided with the Milky Way 8 to 10 billion years ago. This galaxy, about a quarter the size of the ancient Milky Way, didn't just merge gently, it crashed in at an angle, scrambling stellar orbits and potentially destroying existing galactic structures. Dr. Amina Helmi at the University of Groningen discovered this ancient collision. The impact was catastrophic. It heated the Milky Way's disk, scattering stars into the halo. It might have destroyed the galaxy's early bone structure completely, forcing everything to reform from scratch. Evidence of this collision is everywhere. Stars with unusual orbits, moving backward or on highly elliptical paths, are likely debris from Gaia Enceladus. Chemical signatures in old stars reveal which formed in the Milky Way and which are immigrants from the devoured galaxy. But the bones themselves carry the most detailed record. By analysing the ages of stars in different parts of galactic filaments, astronomers can date when structures formed. The current generation of bones appears to be relatively young, most formed after the Gaia Enceladus collision. Dr. Yuan Sen Ting at the Australian National University uses machine learning to read this record. We're training AI to recognise patterns in stellar chemistry and motion that indicate different formation events. It's like teaching a computer to read tree rings, but for the entire galaxy. The archaeological record reveals waves of star formation triggered by various events. 13 billion years ago, the first stars form in the proto-Milky Way. 10 billion years ago, the Gaia Enceladus collision triggers massive star formation. 6 billion years ago, the Sagittarius dwarf galaxy's first passage causes another burst. 2 billion years ago, a possible collision with another unknown dwarf galaxy. 500 million years ago, Sagittarius passes again, possibly triggering the formation of our Sun. Each event fractured existing structures and created new ones. The galaxy we see today is like a city built on the ruins of previous cities, each layer telling part of the story. Dr. Melissa Ness at Columbia University reads chemical signatures in stellar spectra. Every star is a time capsule, preserving the chemical composition of the gas it formed from. By analysing millions of stars, we can map how the galaxy's chemistry evolved over time and space. The bones themselves show chemical evolution. Older filaments contain mostly hydrogen and helium, while younger ones are enriched with heavier elements from generations of stellar death and rebirth. Some bones show chemical gradients along their length, recording how enriched material flowed through the galaxy. The fracture patterns are particularly informative. Recent breaks show sharp edges and scattered debris. Ancient breaks have been smoothed by billions of years of gravitational evolution. Some fractures have healed, with new structures bridging the gaps. Others remain as permanent scars.
The more we study the Milky Way's bones, the more it becomes clear that our galaxy isn't just a collection of stars and gas. It's a living system that grows, adapts, heals, and evolves. The bones are both the skeleton and the circulatory system of this vast organism. Dr. Eve Ostreicher at Princeton University studies the galaxy as a complex system. The Milky Way exhibits properties we associate with life: self-organization, homeostasis, response to stimuli, adaptation. It's not conscious, of course, but it's far more than just physics playing out. It's a system that maintains and reproduces its own patterns. The self-organization is evident in how structures form spontaneously from chaos. Turbulent gas naturally organizes into filaments. Random stellar motions synchronize into spiral patterns. What starts as disorder becomes order through the interplay of fundamental forces. The galaxy maintains homeostasis, a stable internal environment despite external changes. When star formation uses up gas, dying stars replenish it. When structures are destroyed, new ones form. The galaxy has maintained roughly the same star formation rate for billions of years, despite dramatic events.
Dr. Bruce Elmergreen at IBM Research studies this galactic homeostasis. There's a feedback loop between star formation and gas dynamics. Too many stars form, they blow away the gas, star formation drops. Too few stars, gas accumulates, star formation increases. The galaxy self-regulates like a thermostat. The response to stimuli is clear in how the galaxy reacts to collisions and interactions. When the Sagittarius dwarf passes through, the disk rings like a bell. Spiral arms tighten or loosen in response to gravitational perturbations. The galaxy doesn't just passively experience events, it responds dynamically. Adaptation is perhaps the most remarkable property. After each collision or disruption, the galaxy doesn't just repair itself, it often comes back different, sometimes stronger. The spiral arms that formed after the Gaia-Enceladus collision are more pronounced than what likely existed before. The galaxy learned, in a sense, a new structural configuration. Dr. Katherine Johnston at Columbia University sees parallels with biological systems. Galaxies evolve through a kind of natural selection. Structures that are stable persist. Unstable structures disappear. Over billions of years, galaxies evolve toward configurations that can survive in their environment. The bones play a crucial role in this living system. They channel nutrients, gas and dust, to where they're needed, remove waste products, hot gas from supernovae, provide structural support against gravitational collapse, serve as nurseries where new stars are born, connect different parts of the galaxy into a coherent whole. The fractures and breaks in the bones aren't just damage, they're part of the living process. Like bone fractures in animals that heal stronger at the breakpoint, galactic fractures often become sites of intense star formation, creating new structures that can be more robust than what existed before. Dr. Daniela Calzetti at the University of Massachusetts Amherst studies star formation in fractured regions. Breaks and collisions compress gas, triggering starbursts. What looks like destruction is often creation in disguise. The galaxy uses trauma as an opportunity for renewal. Where exactly does Earth sit within this vast skeletal structure? We're not in a bone, we're in a fracture. Specifically, we're inside the local bubble, a cavity blown in the galaxy's structure by ancient supernovae. But this apparent void isn't empty or isolated. We're connected to the galactic skeleton in ways we're only beginning to understand. The Sun orbits the galaxy every 220 million years, a journey that takes us through different galactic environments. Sometimes we pass through spiral arms, dense with gas and dust. Other times we travel through relatively empty regions. Right now, we're in a unique position, at the edge of a fractured bone, surrounded by stellar nurseries triggered by the very explosions that cleared our local space. Dr. Catherine Zucker maps our local neighborhood. We're like someone living in a house where the walls have been blown out, but we can see the frame structure all around us. The Radcliffe wave passes just 500 light-years away. The Perseus molecular cloud is to one side, the Orion complex to another. We're surrounded by active star formation, but sitting in a quiet pocket. This position might not be accidental. Research suggests that life-bearing planets might preferentially form in such cleared regions. The supernovae that create these bubbles also enrich the surrounding gas with heavy elements necessary for rocky planets and complex chemistry. The cleared space protects young planetary systems from disruptive close encounters with massive stars. Dr. Fred Adams at the University of Michigan studies habitability in the galaxy. There might be a galactic habitable zone, just like stellar habitable zones. Too close to the galactic center, radiation and stellar encounters destroy planets. Too far out, there aren't enough heavy elements. Too deep in a molecular cloud, planets never see starlight. But in fractured regions like ours? Perfect. Our passage through different galactic environments has consequences for Earth. When we pass through dense molecular clouds, the influx of cosmic dust might trigger ice ages. Passages through spiral arms with their higher radiation might cause mass extinctions. The galaxy's skeleton shapes not just where we are, but what happens to us. Dr. Nir Shaviv at the Hebrew University of Jerusalem has correlated Earth's geological record with our galactic journey. We see patterns. Every 140 to 150 million years, corresponding to spiral arm passages, there are peaks in extinction rates and climate changes. The galaxy's structure directly influences life on Earth. Looking forward, our position will continue to evolve. In about 13 million years, we'll pass through the Radcliffe Wave again. In 30 million years, we'll enter the Perseus spiral arm. Each passage will bring new challenges and opportunities, but perhaps most remarkably, we're beginning to influence the structure around us. Human technology now produces radio signals that propagate into space, creating an expanding bubble of electromagnetic radiation. While tiny compared to galactic structures, it's a sign that life can affect its cosmic environment. Dr. Jason Wright at Penn State speculates, advanced civilizations might intentionally modify galactic structures, clearing bubbles for safety, channeling gas flows for resources, even triggering star formation. The broken and reformed structures we see might not all be natural. We might be looking at cosmic engineering projects we don't recognize. What happens next? The Milky Way's bones will continue to break, heal, and evolve. And we're approaching several significant events that will reshape the galaxy's skeleton dramatically. The most imminent, in cosmic terms, is the ongoing merger with the Sagittarius dwarf galaxy. This small galaxy has already passed through the Milky Way's disk multiple times, each passage causing disruption. But Sagittarius is dying. Within the next billion years, it will be completely absorbed, its stars scattered throughout our galaxy's halo. Dr. Pierre-Alain Duc at the University of Strasbourg models this ongoing merger. Each passage strips more stars from Sagittarius. It's like watching a comet dissolve, but the comet is a galaxy, and the process takes billions of years. The final passage will likely trigger another burst of star formation throughout the Milky Way. But the big event is the collision with Andromeda. Our nearest large galactic neighbor is heading straight for us at 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and eventually merge into a single elliptical galaxy. This collision will completely destroy the current skeletal structure. The elegant spiral arms will be pulled apart. The organized bones will be scrambled. The ordered circulation will become chaotic. But from this chaos, new structures will emerge. Dr. Roland van der Marel at the Space Telescope Science Institute has simulated this collision. It will be spectacular, but not immediately catastrophic. The galaxies will pass through each other, swing back, and merge over about 2 billion years. The bones will be shattered, but new, larger structures will form in the merged galaxy.
The discovery of the Milky Way skeleton and its fractures changes how we see our cosmic home. We're not randomly placed in an indifferent universe. We're precisely positioned in a carefully evolved structure, products of billions of years of galactic evolution, witnesses to an ongoing cosmic story. The broken bones of our galaxy tell us that destruction and creation are partners in the cosmic dance, that structures spanning hundreds of light years can be both incredibly strong and surprisingly fragile, that our galaxy remembers its past in the positions of its stars and the patterns of its gas, that we live inside a fracture that gave us life. As technology improves, we'll see these structures in ever greater detail. The upcoming Roman Space Telescope will map the galaxy's bones in infrared. The square-kilometre array will trace magnetic field lines through the skeleton. Future space missions will chart gas flows and dark matter structures with precision we can barely imagine. Each discovery will add to our understanding of the vast structure we inhabit. We'll learn to read the galaxy's history in its broken bones, predict its future from its healing patterns, and understand our place in its grand architecture. But perhaps the most profound realization is that we're not just observers of this cosmic skeleton, we're part of it. The atoms in our bodies were processed through the galaxy's circulation system. The star that warms us formed from gas compressed by galactic structures. The planet beneath our feet condensed from dust enriched by the galaxy's chemical evolution. We are the galaxy, examining itself. Broken bones studying broken bones, fractures contemplating fractures. Through our telescopes and theories, the Milky Way is developing self-awareness, learning its own structure, understanding its own story.
The journey that began with Dr. Goodman staring at an impossible structure on her computer screen has become humanity's journey into understanding our cosmic anatomy. We've discovered that we live inside a galaxy that's more like a living organism than a collection of stars, more like a healing patient than a static structure, more like a story still being written than a finished book. The Milky Way's fractured cosmic bones aren't just structures in space, they're the architecture of our existence, the framework of our cosmic home, the skeleton that holds the galaxy together while allowing it to evolve. Every break tells a story, every healing shows resilience, every new structure demonstrates creativity. As you look up at the night sky, remember, you're not seeing random stars but organized structures, not empty space but invisible bones, not a static picture but a dynamic, evolving, living galaxy that's been building and breaking and rebuilding for 13 billion years. And in one small fracture, on one small planet, around one ordinary star, the galaxy has produced something extraordinary. Minds capable of comprehending the very structures that created them. We are the galaxy understanding itself, broken bones contemplating the nature of breaking and healing on cosmic scales. The story of the Milky Way's fractured cosmic bones is our story, a tale of destruction and creation, breaking and healing, chaos and structure. It's a story that began billions of years before Earth formed, and will continue billions of years after Earth is gone. But for this brief moment, we're here to witness it, study it, and marvel at our place within it. The galaxy's bones will continue to break and heal, its circulation will continue to flow, its structure will continue to evolve. And if we're wise, we'll continue to learn from it, understanding that resilience comes not from avoiding fractures, but from healing stronger, that creation often requires destruction, and that we're all part of something far grander than ourselves. This is the gift of discovering the galaxy's skeleton, the knowledge that we're not alone in empty space, but embedded in living structure, not randomly placed but precisely positioned, not separate from the cosmos but woven into its very bones. The Milky Way's fractured cosmic bones tell us we're home, in a galaxy that's broken but healing, violent but creative, ancient but still evolving, just like us. Thank you for joining me on this journey through the hidden architecture of our galaxy. If this exploration of the Milky Way's cosmic skeleton fascinated you, please subscribe to follow more adventures into the mysteries of our universe. I'd love to hear your thoughts in the comments. What amazed you most about our galaxy's hidden bones? What questions do you still have about these vast structures we're only beginning to understand? And remember, every time you look up at the night sky, you're seeing not just stars, but the vast skeletal structure that connects us all. Until next time, keep looking up and wondering.